Hey guys, welcome back. Naj Kazi here. First of all, I would like to wish you a very happy new year. Second of all, I've got a very exciting video for you today. I'm going to go deep into the layer 2 concepts, advanced layer 2 concepts like CDP, LLDP, and Spanning-Tree Protocol. It's going to be an exciting one, so hold on to your seats and let's roll. Welcome to CCNA 200-301 course. Today, I'm going to discuss Section 2, Part 2, LAN, wired and wireless. In particular, we're going to focus on advanced LAN switching concepts. Here are the topics I plan on covering today. First, CDP. Second, STP, PVST, and RSTP. Third, STP optional features. Fourth, Ether channel. And finally, I'll wrap it up with inner VLAN routing. So what is CDP? CDP stands for Cisco Discovery Protocol. As the name gives it away, it's Cisco proprietary, meaning only Cisco devices speak this protocol. The whole purpose of this protocol is to help discover neighbors. So for example, if I'm a switch and I have other switches and routers plugged into me, when CDP is enabled everywhere, I can see who are the neighbors that are connected to me. Typically, network engineers and consultants use CDP to verify physical connectivity of a network. And I'll give you an example of how that works on a switch CLI in a moment. The way CDP allows discovery to happen is through CDP messages. And these messages are sent across all ports on all routers and switches by default. Another interesting tidbit, Cisco IP phones use CDP to learn both the data and voice VLAN IDs that are configured on that access switch port. And finally, LLDP or Link Layer Discovery Protocol is a competing standard to CDP and is defined in IEEE 802.1ab standard. If you happen to have any non-Cisco switch in your environment, whether Arista, Juniper, or you name it, any other switch, it runs LLDP for the purpose of discovering neighbors. So what you would have to do in that instance is, if you have a mixed environment, Cisco and non-Cisco, you should actually run LLDP everywhere instead of running CDP. Because this way, whether you're connected to a Cisco neighbor or a non-Cisco neighbor, you can discover and see what's going on. Now, just by looking at these bullets, it's probably not sinking in much. Let me jump right into the CLI so I can help you crystallize how CDP works. Here I am on switch 1. Here's the magic command you want to know. Show CDP neighbors. On switch 1, what I can see by running this command is that I've got 3 different devices that are plugged into me. And those 3 devices are, I've got switch 2 plugged into me over fast Ethernet 0/12. And the capability flag here corresponds to a switch because it's a switch. And the platform is Catalyst 2960. And the remote port ID, the port ID of the remote switch that's plugged in is this. Similarly, S3 right below it is connected over fast Ethernet 0/13. The flag is also S. And platform is Catalyst 2960. Remote port happens to also be fast Ethernet 0/13. Finally, R1. Our local interface is Gigabit Ethernet 01. Flag is set to R because it's a router. It's an ISR 4300 router. And the remote interface on that router that is pointing toward us is Gigabit 000. Now, another interesting command that gives us a lot more detail about our neighbors is show CDP neighbors detail. Now, one thing I would like to draw your attention to here is that so here we're looking at router 1, and I can see the IP address of router 1, so that's pretty neat. Right? So as you can imagine, if I've got other devices plugged in and I'm walking into an environment completely cold as a consultant, I had never worked in this environment before, I have no clue how this environment is set up. By using show CDP on different switches and routers, I can start to map out how the network is set up. I can actually create a diagram with physical connections so I can see how it's all interconnected. In addition, as a bonus, I can also specify the IP addresses of the devices as well. So really, really cool feature. Now I'm going to warn you, it works wonders if it's a small environment. But the minute you start looking at gigantic global environments, it's not going to work. If you have hundreds of switches or thousands of switches, it's insanity to go to each switch and start mapping things out. You're going to go crazy. Instead, there are other tools that you can use for monitoring purposes and things like that. But at the same time, typically larger networks, the network engineers that manage those environments have really good documentation, or they're supposed to have really good documentation. That includes really nice Visio diagrams, some additional documentation that talks about the purpose of each device in the network, and things of that nature. Now, if you want to disable CDP on a switch, we type in no CDP run command. And when we do that, this essentially kills CDP on the entire switch, which means we're not going to be able to see our neighbors, and vice versa. Our neighbors are not going to be able to see us because the CDP packets, CDP messages, CDP frames have been killed. CDP basically, just so you know, runs at layer 2. This disables it at a global level on all the ports. But let's say if we didn't want to do that, we would do CDP run. So we enable it again on this switch. But what we can do instead is we could go to a particular port, and at the sub-interface level, we can do no CDP enable. And what that would do is kill CDP on this interface only. So there are two different ways of doing it. One at a global level with no CDP run, or we could do it at a per interface level by typing in no CDP enable. Now, if you wanted to enable it back on this interface, all you would have to do is just delete that keyword no in front of the command. Just type in CDP enable and boom, it's gonna enable CDP again on fast01. Now, that being said, if you wanted to set up LLDP on our switch, we can do that by first disabling CDP and by enabling LLDP run. And when we do that, it's going to enable LLDP on the switch. Now we're going to have to type in the same command on all the other switches and routers to make sure we have a standardized environment and we're sending same type of packets and we're able to see each other. So you're going to have to go to all the remote devices and do the same thing. I'm not going to go much into LLDP because it's very similar to CDP. I just wanted you to understand conceptually how that works. Now, let's talk about STP. What is STP? It stands for Spanning-Tree Protocol. It's a layer 2 protocol, and the entire purpose in life for Spanning-Tree Protocol is to create a loop-free topology by blocking redundant links. Why do we need to do that? Well, in a network, we need redundancy. Without redundancy, we find ourselves in a bad place. So to give you an example, let's say we have a couple of switches here. So we got switch 1, switch 2, switch 3. They're all connected to each other back to back in a daisy chain style. And we got host A here connected to switch 1, and we got a server 1 connected to switch 3. Now, if this guy, let's say Bob, wants to connect to the server, he's going to have to go this direction. Well, what if this link fails? The entire communication fails. What if this link fails? The entire communication fails. That is unacceptable. So what we do is we create redundancy by having a scenario like this where we have redundant links. So if any of these links went down, we still had another path to go from source, from Bob to the server, from source to destination, right? That's the entire idea of having a network. But the issue is that when we do this type of redundancy in a layer 2 network without running spanning tree protocol, we run into some major issues. And there are 3 big issues that I would like to bring to your attention. Issue number 1, broadcast storm. Issue number 2, CAM table instability. Issue number 3, transmission of multiple frames to the destination. Well, what does that mean? Let me explain on the next slide. In a scenario like this, where we have host A connected to a switch, host B connected to another switch, and these 2 switches are connected to each other via a single link, that's not a problem. They can talk to each other all day long, even without running spanning tree, not an issue. But the minute we add this second link into the picture here, well, we got ourselves a problem if we're not running STP. What's going to end up happening is when host A wants to talk to host B, it's going to send an ARP message, address resolution protocol. So remember, ARP, we already have a layer 3 IP address of the device you want to talk to, in this case host B, but what we do not have is the layer 2 MAC address. That's the question mark. So what we end up doing is we construct an ARP frame and we send it out, and at layer 2 of this ARP frame, if you were to zoom into it, what we'll see is that the destination MAC address field is set to all Fs because host A does not have the entry of MAC address for host B in its ARP table. That's why it sent the ARP message to begin with. When that happens, this switch in the middle, let's say switch 1, and the top one is switch 2, switch 1 is going to get it. And it doesn't understand layer 3 at all. So it's only going to look at source and destination MAC address. When it looks at the source MAC, it goes ahead and puts the MAC address of A in its CAM table or MAC address table. However, when it looks at the destination field, it realizes that it does not have that in its CAM table or MAC address table. So it sends out a broadcast. So this is the port that it initially received the request on. It's not going to send the broadcast out here. However, it will flood this frame out all the connected ports. So switch 2 is going to get that frame twice over each link, and host B is going to get that frame. Now when host B gets that frame, it's going to respond back with its MAC address, because when it looks at the layer 3 destination IP field, that IP address will match its own IP. So it responds back to host A with its MAC address. When it does, switch 2 learns that MAC address and puts it in its CAM table or content addressable memory table. We have redundant links, so the frame is being sent out both links in all directions. When switch 2 gets that frame that was initially sent by switch 1, it's gonna send it back out to switch 1 again. It creates this kind of broadcast storm where the frame keeps looping around the network over and over and over again. And unfortunately, at layer 2, we do not have what's called a TTL value or time to live value, which we do at layer 3, but at layer 2, we do not have TTL at layer 2. So what that means is the frame can literally loop around forever and ever, bringing the network to its knees unless you turn off the switches or you break one of the links or you do something manually to stop that from happening. So that's the first problem we get. The second problem we have to deal with is the CAM table instability. So let me explain. Let's say if this is port 1 and this is port 2. When switch 1 sends that frame out to switch 2 with the source MAC address of host A, not only switch 1 is going to learn it, but switch 2 will also learn it because of the fact that that source MAC address is in that layer 2 header field. So it's going to grab it and insert it into the CAM table. That's what switches do. They learn MAC addresses. Let's say if that frame arrived maybe a few milliseconds before arriving over port 2, switch 2 is going to have confusion in its MAC table. It's going to say, well, I've got MAC address A available over port 1. But when the same frame arrives a few milliseconds later, it's going to get confused and go, no, it's not over port 1. It's actually on port 2 is where MAC address of A lives. And when it does that, it's going to keep switching back and forth as it continues to get frames. And this causes MAC instability because you're going to keep switching back and forth between port 1 and port 2. And finally, because we have these redundant ports and multiple frames, the host may end up getting multiple copies of the same frame, and it would cause issues. The application that host B is running might actually crash because it may not know how to handle duplicate frames. So these are the three big issues that occur in a network when there's no spanning tree running. Now let's jump into STP fundamentals. As I mentioned, it's a link layer protocol. It's a layer 2 protocol designed to ensure loop-free topology. It's defined in IEEE standard 802.1d. So it's an open standard. It's not proprietary to Cisco, which is good. Switches use special frames called BPDUs or probes to exchange information about bridge IDs and route path cost, and we'll talk about those details momentarily. You'll be an expert in a few minutes. But before we get there, what are BPDUs? They are Bridge Protocol Data Units. BPDUs are essentially spanning tree advertisements. BPDUs are sent out all active ports on a switch every 2 seconds by default. However, on the non-root bridge, BPDU hello messages are sent based on the timer configured on the root switch. So let's say if on the root switch you change the timer to a non-default value, the non-root bridges will adhere to that non-default value. And remember, the main function of STP is to do what? To discover loops in the network and find the most efficient way back to the root and block the redundant links. Now let's talk about bridge ID. Each BPDU frame contains within it two major fields, a bridge priority and switch's MAC address. Combined together, it's called bridge ID or BID. So here we get to see that we have a bridge ID of 8 bytes altogether at layer 2. We're basically looking at a layer 2 header of the BPDU. We got the bridge priority here, which is 2 bytes, which means it's a value anywhere from 0 to 65, 535. Default is right in the middle. And the other piece of it is the MAC address, which is 6 bytes. And that MAC address is derived from the backplane of the switch or the supervisor. So if it's a fixed switch, this MAC address is derived from the backplane. If it's a modular switch with supervisor modules in it, it's going to derive its MAC address from the supervisor module. Default bridge priority is 32,768, and it can be modified in the increments of 4096. Now, one thing I want you guys to keep in mind is when it comes to bridge priority, lower value is better. One more thing about BPDUs, there are two different types of BPDUs. You have configuration BPDUs and you have topology change notification BPDUs. Configuration BPDUs are originated by the root bridge and they flow outward away from the root, whereas the topology change notification BPDUs flow toward the root bridge for providing topology change updates. Now let me explain what I mean by that right here. If this guy up at the top ends up becoming a root bridge of our network, what that means is all of these switches here in our environment are gonna try to find a way back to the root without causing loops. So what that means is this link will get blocked, this link will most likely get blocked, and access switch 1 at the bottom will go through distribution switch 1 up to core switch 1. And access switch 2 is going to go to distribution 3 up to core switch 1. So the idea is that we always want to have a single path toward the root bridge, and this inherently helps us avoid loops because we're only going in one direction and there is no opportunity for the same frame to kind of boomerang or loop back around to us because we're only going in one direction. So that's the whole idea of STP. So we have this root bridge and everybody kind of gravitate towards this root bridge and it becomes the center of the universe for our STP domain. Now, as I mentioned, there are two different types of BPDUs, config BPDUs and topology change notification BPDUs. Now, configuration BPDUs are sent by the root bridge. So the root bridge actually sends configuration BPDUs, and they're sent down this way, downstream. Another terminology I want you to understand, when we go up toward the root, that's upstream. When we go down from the root down to the other switches, that's called downstream. So the core switch sends configurations BPDUs downstream, whereas the topology change notification BPDUs are sent upstream by the non-root bridges to inform the root bridge of any change that happened in the network. Now let's talk about 3 steps of initial STP convergence. Very, very critical to understanding STP. First thing that happens is we must select or elect one root bridge. So as soon as you have these multiple switches in your environment connected together, they come online, the first thing they want to do is they go through a series of steps. And the very first step in the process is to elect one root bridge, or the king of the hill, if you will. All switches exchange BPDUs, and the switch with the lowest bridge ID ends up becoming a root bridge by default. So for example, in the topology that we have here, this bottom switch ends up becoming a root bridge. And the reason for that is because it has the lowest MAC address. So remember, the bridge ID is composed of 2 components. We got the bridge priority and we got the MAC address. And this right here is the bridge priority. So if you were to look at all these, the reason switch A became the root bridge is because from a hexadecimal perspective, A is lower than B or C. Because A in decimal is 10, whereas B in decimal is 11, C in decimal is 12. So this guy becomes the root bridge. However, root bridge election can be manipulated by changing the priority in bridge ID, since MAC address is hard-coded into each switch. So because we can't change MAC, the only way to influence the election process is by changing the bridge priority. And I'll show you that on a CLI in a moment. By the way, a pro tip, because the lowest number MAC address ends up winning the election, what that means is the oldest switch in your network that you bought in 1990s that is still out there sitting in a closet somewhere most likely will end up becoming a root bridge if you don't define a root bridge yourself. So it's a bad place to be, something you have to keep in mind. And I've seen some networks and very, very ugly designs where network administrators didn't really pay attention to what was happening and they let spanning tree do its thing. By default, it's not good. It's very bad. And I'll give you a couple of examples, including a visual example to show you how bad it is. All right, step number 2. After electing the root bridge, we want to elect root ports. Root ports are elected on the non-root bridges. It's the closest port to the root bridge. Every non-root switch needs to have one root port and only one. The third step in the initial convergence is, so first we elected the root bridge. Second, we elected the root port. Third, we want to elect designated ports. After the root ports are assigned, switches allocate one designated port per link. Designated port equals forwarding port. So if you were to look at the topology here, considering the bottom switch is the root bridge, both switch B and C will have a root port pointing to the root, and then switch B will have a designated port pointing to switch C. However, the port on switch C going toward B is going to be in a blocking state. And one thing I want to touch base on when it comes to this blocking port is that the data plane traffic on the blocking port is dropped. Only control plane traffic is allowed, because control plane is a spanning tree, right? And I actually did a video on the topic of control plane versus data plane. Watch my SDN video, software defined networking video, to learn more. But once again, on the blocking port, there's no user data traffic that's sent, because again, the idea is we want to avoid frames from looping around the network. Quickly, here's our network topology that we'll be working with today when it comes to spanning tree. As you can see, we got a couple of switches connected in a triangle, and we got each switch has a router hanging off of it. Now, before I jump into CLI, let me finish talking about the election process and then jump into CLI, because I think that will help crystallize some of the concepts that we just talked about. So how STP elects the root port per switch. First, as I mentioned earlier, we must elect a root bridge, and this is the switch with the lowest bridge ID. It ends up becoming the root bridge. Once that happens, that's out of the way. The next thing you want to focus on is the root port election. First step here is the lowest cost to the root bridge. In case of the same cost on multiple links, so for example, if the switch at the top is the root bridge and the switch at the bottom is a non-root bridge, if I have two links like that, both are 100 meg links, the cost is the same on both links. So I can't use that criteria to elect a root port, the most efficient port going to the root bridge, right? I cannot do that because the cost is the same on both links. What we do is you look at the lowest sender bridge ID, and if that is also a tie, then we finally look at lowest port priority. Now this is very, very random. This is an absolute tiebreaker, and you will absolutely finish the election process here because each port has a unique port priority. That said, so as I mentioned, the cost, there's an inverse relationship between the bandwidth and the cost. So for example, a 10 meg link is a 100 in STP cost, but a 100 meg link is 19 in STP. A gig E link is 4 in STP, and a 10 gig link is 2 when it comes to STP cost, which means the lower the STP cost, the better and the more preferred the link would be. That said, let's jump right into the CLI. So here I'm on switch 3. Let me go ahead and quickly look at a couple of commands. Show spanning tree. That's the first command I want to look at. Here, what it's showing me is that this bridge is the root. What that means is that I am the root bridge. So S3 in our topology is the root bridge, this guy right here. And a couple of things I would like to bring to your attention here. First, like I said, this bridge is a root. That's important. Here's the bridge priority, and the MAC address, which is right here, should be the same as here because we are the root bridge. And we see things like, the hello timer, like I said, 2 seconds. The max age timer is 20 seconds. There's a forward delay of 15 seconds, and then aging time is 20 seconds. A couple of other things I want to draw your attention to is that we're connected to a couple of different devices here on our network that are also running spanning tree. So because we're the root bridge, we've got Fast Ethernet 13 specified as a designated port, which means it's in forwarding status. And the cost is 19 because it's a 100 meg link. And we see the port priority number here, 128.13. And Fast Ethernet 0/23 with the cost of 19, which is also a 100 meg link. We also have a gigabit Ethernet link connected to our router. And the cost there is 4. There's no point in running spanning tree to the router because routers don't speak spanning tree. They understand layer 3. So we can ignore the bottom link, but the key is the first 2 links. Now let's see what we see on the other switches in our environment. Here I am on switch 1, and let's do show spanning tree. And what I see here is that you're running spanning tree, which is the IEEE version. This is once again open standard, meaning if you had a non-Cisco switch, we would be able to speak that to them. Root ID priority is set to 32.769. This is the MAC address of the root bridge, and our cost to get to the root bridge is 19. And we're using port 13 to connect to the root bridge. Whereas the bridge ID piece shows us our own properties as a local switch. So as S1, my priority is 32.769. As switch 1, my MAC address is this. And then all these different timers, STP timers. Another thing to note here is on S1, once again, forget about the bottom one because that's router. So we don't need to worry about spanning tree with the router. You can just ignore that. Let's just focus on the top 2. So Fast Ethernet 0/12, that's my connection to switch 2. That's a designated port, meaning I'm able to forward traffic on this link. And the cost is 19, which is once again 100 meg. Fast Ethernet 13 is a root port. That's the port I'm going to use to connect and communicate back to the root. And the port cost is 19. Looking at this diagram here, S1 makes this the root port and makes this the designated port toward S2. Well, why is that? Couple of things. Well, the guy at the top, S3, is the root bridge, right? So as you can visually see, S1 is physically plugged into S3. And this port right here, this link, is 100 meg. And 100 meg, if you remember the chart that I showed you earlier, is 19 STP cost. So that's the cost of going to S3. Now, what's the cost of S1 connecting to S3 via S2? Well, that's 19 here for this link and 19 here for this link. Well, that's 19 plus 19 equal 38. So that's a total cost of 38. So of course you're going to prefer the lowest cost because lower is better. Plus you're physically connected to it, so it makes sense. So this is one way of visually looking at and making sense of how STP operates. Another is to do a bit of a deeper dive. But before I do that, now let's go ahead and jump on the CLI of switch 2 so I can show you spanning tree there, and then I'm gonna do a deeper dive. Let's quickly look at switch 2 and see what's going on here. So show spanning tree on this switch shows me that the root ID is this MAC address. It's not us because it doesn't say this is the root bridge, right? So remember that, right? So the keyword, this is the root bridge, here in this portion verifies that us locally are the root bridge. But in this case, this switch is not the root bridge because we can clearly see that there is a MAC address and there's a cost associated with that, and it's showing us the bridge is available over port 23. And our bridge ID, another visual verification is that the MAC address here is different than the MAC address here. So this is our local MAC address, and the MAC address above here is the root bridge's MAC address. So that's another visual verification that we're not the root bridge, somebody else is in the network. Now something really interesting is happening here. Once again, forget about the router, right? We don't want to look at that because that will only confuse us. Let's only look at the other two switches that are connected in this environment. Switch 2 is connected to switch 1 over fast Ethernet 12. The role here is blocking, and the cost is 19. So this link right here is actually being blocked, meaning no frames are going to be sent, no data is going to be sent, no data plane traffic at all. Only BPDUs will be received, but no traffic, user traffic will be received. Fast Ethernet 0/23, on the other hand, which is switch 2's connectivity to the root bridge. Going back to the diagram here, this is the root port, and this is in blocking state, this right here. Because remember, in STP, we must have a port that's blocked. Otherwise, we'll have a situation where frame goes out and loops around the network forever and ever and ever, and brings the network down to its knees. Completely kills the CPU and memory and chews up pretty much all the capacity on all the devices, and that's a bad place to be because there's no TTL value at layer 2. So the frames never die. They'll live forever. That said, let's quickly figure out why in our topology this guy became the root bridge and this guy had a designated port allocated to it in this direction, and this guy had a blocking port. Why is that? How did this happen? Well, remember, it goes back to the bridge ID, which is a combination of two things: bridge priority and the MAC address. Well, bridge priority by default is set to 32.768. That's a default value on all Cisco switches, and the MAC address is the only tiebreaker at that point. And remember, the older the switch is and the lower the MAC address is, the more preferred, and the lowest MAC address ends up becoming the root bridge. Now, let's find out if that is the case. Now, let's go ahead and grab MAC addresses of all of these switches and do the math and figure out how they decided to do what they did. So if we were to go to our topology here, and here are all the MAC addresses that I grabbed off of these switches. I did the hexadecimal math in my last video, so check that out, but I'll give you a quick walkthrough of it again. If we were to do an eyeball comparison, you can clearly see that in all of the MAC addresses in the first octet, the first two values are all zeros. Where things start to differ is the third value right here. So as you can see, switch 3 became the root bridge. So the reason it became a root bridge is because if you look at the values here, 3 is the lowest out of all these. 3, then 9, and D in hexadecimal is actually 14. That's why it's all based on the MAC address. Because once again, we only have two things to choose from, either the bridge priority or the MAC address. Because bridge priority is the same on all the Cisco switches by default, the tiebreaker comes down to the MAC addresses. That's why switch 3 was elected as a root bridge. Now let's quickly talk about spanning tree switch port states. There are 5 different switch port states. Number 1, blocking. In order to avoid loops, switch puts a port in a blocked state. Makes sense. We just looked at a blocking port a moment ago. It takes 20 seconds for STP to transition a port from blocking to listening state. The next state happens to be the listening state. Here the port stays in this mode for 15 seconds before next step. Switch sends and receives BPDUs when it's listening. In the learning state, port stays in this mode for about 15 seconds. Switch populates the CAM table in this mode, so meaning it's learning the MAC addresses. Then the next stop is forwarding state. Port starts forwarding traffic here. Another state which is not officially part of the port state, but it's definitely there, is disabled, when port is manually shut down, when you type in the shutdown command, it's considered to be disabled. And at that point, it's not participating in STP because it's been manually shut down. Now, let's add up all the timers to see how long it takes for the port to come up. So we're in blocking state for about 20 seconds, listening for 15, learning for 15 seconds. Finally, we're forwarding. If you were to add it up, 20 plus 15 is 35. 35 plus 15 is 50. Total transition time is 50 seconds, believe it or not. When you have a link failure in a spanning tree environment, it takes 50 seconds for the existing links to reconverge. What does that mean? Let me quickly visually explain this to you. If I have a switch here, and if I have a switch here, and a switch here, they're interconnected like this. If this is the root bridge, and this has a designated port, and this is blocking right here. If this link goes down, which is the root port, if this goes down toward the root bridge on this particular switch, let's say this is switch 2, this is switch 1, and this is switch 3. If this root port goes down for whatever reason, it's going to take us 50 seconds to reconverge and reroute traffic across switch 1 to get to switch 3. Now, by today's standards, 50 seconds is bad. It's really, really bad. To fix that, there are enhancements that were made to the STP protocol. Now keep in mind, STP has been around since 1990s, so it's been around a long time, so enhancements had to be made. Finally, I've got this real-world behavior for you when it comes to STP. So let's say you just set up a brand new network and you had some old switches and you got a bunch of new switches that you kind of put together and created this network, and you connected them up like the way you're seeing in this picture. What's going to end up happening is that through the magic of STP, the switch all the way up at the top is going to end up becoming the root bridge. Reason for that is because it has the lowest MAC address, right? All the other values are the same when it comes to the priority, root bridge priority. That's the same. The only difference is the MAC address. Well, the next step that happens is we're going to have root ports that are going to go toward the root, and then we're going to have a bunch of blocked ports and designated ports. Well, if I were to eliminate all the redundant links that were blocked, look at how suboptimal this network looks when we let STP do its thing. First of all, this switch up at the top is an access layer switch. Access layer switch should never be a root bridge, because root bridge is the one that is, remember, at the center of the universe. So all the traffic must go through the root bridge to get to the other switches. So in this environment, we're sending all the traffic to a closet switch, an access layer switch. That's a bad idea. Plus, this switch might be 20-year-old. Okay? Whereas these switches right here could be the latest Catalyst 9500 switches. Well, if that's the case, this is such a waste, because we have switches that are worth hundreds and thousands of dollars versus a switch that was bought 20 years ago that's virtually worthless at this point and is a choking point in the network, because remember, it only has 100 meg links, whereas these guys here could have 1 gig, 10 gig. Switches these days have up to 100 gig type of connectivity. We are right on the heels of 400 gig. So that's a bad design. You do not want to let STP do its thing by default, because, like I said, it automatically picks the lowest MAC address. And if you look at how the manufacturer IDs work with MAC addresses, whenever a manufacturer starts producing switches, it starts off sequentially. So it starts off with a number, and then from there it continues to add more values to it. So by that token, what that means is the newer switches are going to have a higher MAC address, and the older switches will have a lower MAC address. So that's a huge problem. Instead, we should manually pick these core switches, make one the root primary, and make the other the secondary root, and go from there. Thanks for sticking around. By the way, there's a lot more to this video than what you have seen. In order to watch the entire video, you're gonna have to be a little patient because I'm working on designing an entire CCNA course. I'm gonna do an official launch in the next couple of months, but until then, I'm gonna keep putting little nuggets of the CCNA exam out there on my YouTube channel until the course is ready to be published. Hope you enjoyed today's video. If you did, give me a thumbs up, hit subscribe, and I'll see you in the next video.